Hello everyone, my name is Song Cao. I'm a PhD candidate in Yangzhou University in China. It's my honor to share our latest research, MVD memory-related vulnerability detection based on flow-sensitive graph neural networks in ICSE 2022. First, I will discuss the background of our work. As one of the most representative vulnerabilities, memory-related vulnerabilities can result in performance degradation and program crash, severely threatening the security of modern software such as Google Chrome, PDF, and so on. Recently, CWE have reported top 25 vulnerabilities in 2021. As shown in this figure, a considerable number of vulnerabilities are related to memory security, so timely detection of potential memory-related vulnerabilities in projects is particularly important. Many static analysis-based approaches or tools have been proposed to detect memory-related vulnerabilities and shown their effectiveness. They use some predefined vulnerability rules or patterns to search for improper memory operations. However, all of them have two major limitations. First, well-defined vulnerability rules or patterns are highly dependent on expert knowledge, and thus it's difficult to cover all the cases. What's worse, the complex programming logic in real-world software projects gets in the way of the manual identification of the rules, and thus greatly compromises the performance of the traditional static approaches. Recently, benefiting from the powerful performance of deep learning, a number of approaches have been proposed to leverage deep learning models to capture program semantics to identify potential software vulnerabilities. Compared with traditional static analysis-based approaches, we can automatically extract implicit vulnerability patterns from previous vulnerable code instead of requiring expert involvement. As shown in this figure, deep learning-based approaches take source code and bytecode as input to train a detection model to identify whether this code is vulnerable or not. However, the existing deep learning-based approaches suffer from two limitations when applied to memory-related vulnerability detection, as described below. First is flow information under-utilization. Due to the lack of interprocedural analysis, most of deep learning approaches take the function-level vulnerable code as input to extract vulnerability features. However, in real-world programs, operations like calling a user-defined function which realizes memory allocation of free and widespread. For example, this is a typical used after free vulnerability because the memory space pointed by the pointer recurve is released in advance by the memory release statement at line 5. However, it will be used at line 8 to line 13. The semantic may hard to be learned by deep learning models if they are not aware to interprocedural information. The second problem is partially flow information loss in model training, limited by the capability of popular deep learning models in handling multiple relations. Partial flow information is lost during the process of model training. Still takes this vulnerability as an example. To detect this vulnerability, data flow information is necessary. We can capture the precise flow direction of pointer recurve from line 5 to line 8. However, although recent works use graph representations such as CFG, DFG, or PDG for vulnerability features modeling, different flow information is treated equally. A major threat is that in this vulnerability, we can observe that there's another data flow of pointer IO parameters from line 1 to line 8. If we simply treat this different flow information, the model may not learn effective vulnerability patterns. Another limitation is close granularity. The detection granularity of the existing deep learning models is mostly at the function level or slice level. However, developers still need to spend a deal of time in manually narrowing down the range of suspicious statements or operations. Achieving fine-grained detection results is non-trivial. Due to the huge differences between virus vulnerabilities, existing deployment-based approaches for general vulnerability detection have to sacrifice unique semantic features specific to certain vulnerabilities to ensure that the trained model can cover the general characteristics of the majority of vulnerabilities. In comparison with other vulnerabilities, memory-related vulnerabilities are usually fixed with one or several lines of code, which makes fine-grained detection possible. As shown in the motivating example, the premise of identifying the statement at line 5 as vulnerable is that we should know in advance that the pointer released by this statement will be used later. Thus, to distinguish vulnerable codes from others, the neural networks used as detection models should be able to capture sensitive contextual information within flows of vulnerable statements for inference. Thus, from this motivating example, we can get two observations. First, comprehensive and precise interprocedural flow analysis is necessary because it can make our detection model learn more precise code semantics. Second, sensitive contextual information within flows, such as which variable is transferred from a statement to another, helps to refine detection granularity. To solve the above limitations, our solutions are as follows. To fully authorize flow information, we combine PDG with CG to perform interprocedural analysis to model vulnerability patterns. Next, to learn precise code semantics, we propose a novel flow-sensitive graph neural network to jointly embed both statement embedding and flows information. To capture sensitive contextual information for semantic learning. To find detection granularity, we formalize the detection of vulnerable statements as a node classification problem. The workflow of our approach MVD is shown as follows. It consists of two phases, training phases and detection phase. The training phase includes three steps. In step 1, MVD constructs the program dependence graph PDG based on the control and data flow of the program. To capture comprehensive and precise program semantics, MVD extends the PDG with additional semantic information like correlations and return values obtained from topograph CG to conduct interprocedural analysis. Furthermore, to reduce irrelevant semantic noise, MVD conducts program slicing from the program points of interest. In step 2, MVD uses doc2vec to transform the statements of each slice into low-dimensional vector representations. In step 3, MVD uses flow-sensitive graph neural networks. Our work we called FSGN for short, to jointly embed nodes and relations to learn implicit vulnerability patterns and rebalance nodes levels distribution. Finally, a well-trained model is produced for vulnerability-related detection at the statement level. For the detection phase, with interprocedural analysis, the control and data dependence of a target program is first extracted for program slicing, capture program semantics related to memory usage. Then, for each slice, both its unstructured and structured information are used as graph input to feed into the well-trained detection model for vulnerability detection. We will discuss the details of each part in our approach. In feature extraction, our approach constructs a joint graph representation and performs program slicing. We choose two slicing standards, system API calls and pointer variables because they are often related to some improper memory operations. Figure A is an example. It's a typical memory leak vulnerability and leads into procedural analysis to detect. Its corresponding interprocedural PDG and slices are shown in Figure B. It should be noted that, starting from the program point of interest, we perform backward slicing according to both control and data dependence, while forward slicing based only on data dependence because in program memory operations, for example, allocating memory but not freeing it, have been involved in the forward data dependence, and usually, forward control dependence will induce a great deal of irrelevant statements. Then we use the doc2vec to translate source code into feature vectors because doc2vec can provide a more precise embedding of the code statement that will preserve the semantic information. Then we train a model which can learn implicit vulnerability patterns from source code and identify suspicious vulnerable statements. We construct a novel graph neural network learning, flow-sensitive graph neural network for graph learning. The details of our approach are shown in figure. The key insight of FSGN is to jointly embed both statement embedding and flows information to capture sensitive contextual information for semantic learning. FSGN is composed of three parts: graph embedding, resampling, and classification. In the graph embedding phase, we leverage the entity relation composition operations to jointly embed statements, nodes, and multiple flow edges to incorporate edge embedding into the update of node information. For example, to aggregate information from neighbor nodes to update the representation of node 3, initial representations of node 1, 4, 5 are embedded jointly with their incoming edges to preserve some important features from outgoing nodes. However, although we have filtered some irrelevant nodes by programming slicing, the number of non-vulnerable nodes, for example, node 1 to node 4, node 6, node 8, is still larger than that of vulnerable nodes. To generate some sensitive vulnerable nodes to rebalance the distribution, we first utilize a widely used SMOD algorithm to perform interpolation on vulnerable nodes. Then we adopt weighted inner production to generate edges and gives link predictions for sensitive nodes by setting a threshold to keep the connectivity of the graph. If the predicted probability of connection between sensitive node and its closest neighbor node is greater than theta, both the sensitive node and corresponding edge will be put into the augmented matrix of original graphs. Before training the classification model, FSGN adopts one-layer flow-sensitive graph learning block again to update node information. By learning both the unstructured and structured features from nodes and edges, the classification model is employed to distinguish verbal or non-verbal statements. For evaluation, we present four research questions. RQ1: how effective is MVD compared to deep learning-based vulnerability detectors? RQ2: how effective is MVD compared to static analysis-based vulnerability detectors? RQ3: how effective is FSGN for memory-related vulnerability detection? And RQ4: how efficient are MVD and baselines in terms of their time cost for detecting memory-related vulnerabilities? Since existing vulnerability datasets are either not tailored for memory-related vulnerabilities or not sufficient for training dataset for training deep learning models, we manually constructed a new vulnerability dataset which covers 13 common memory-related vulnerabilities for model training and evaluation. The details of our dataset and distribution of different types are shown below. In total, we collected 4,353 vulnerable samples in our dataset. Okay, the overall results of each deep learning-based approach in terms of the evaluation metrics are shown in the following table. Overall, MVD achieves better results and performs of the three referred deep learning-based approaches. Moreover, in terms of all metrics, MVD can improve the best performing baseline design by 5% to 12%. For example, this is a real-world vulnerability in Linux kernel missed by design. It may lead to arbitrary addressed free or double-free vulnerability by attackers because in certain situations, the pointer left info at line 7 can be the same as right info at line 3. However, after right info has been freed at line 9, left info, which is the same as right info, will be used at line 12 to line 3 again. There are two main reasons why this vulnerability cannot be detected by design. On the one hand, due to the lack of procedural analysis, the precise program semantics like memory-free are hard to be captured, causing precise semantic modeling. On the other hand, since design processes multiple flows information by passing information in each individual graph and then integrates them across graphs, left info and right info are treated as different data flows, which causes complex semantic relations difficult to be preserved. Thus, in comparison with the popular deep learning models, MVD achieves better detection performance by fully utilizing flow information based on interprocedural analysis and FSGE. Okay, this is RQ2. This table shows the experimental results of MVD and the static analysis-based techniques. Overall, MVD outperforms all baselines. Further, we also performed a small case study on 30 vulnerabilities randomly selected from our dataset. We can also observe that MVD outperforms all baselines by detecting 17 out of 30 vulnerabilities, including 9 vulnerabilities cannot be detected by baselines, especially in comparison with the best performed baseline PCA. Our approach can detect 8 more vulnerabilities. From this article, we can conclude that with the advantage of deep learning models in mining implicit vulnerability patterns, MVD performs better in comparison with the popular static analysis-based approaches. In RQ3, we conduct an ablation study by replacing our FSGN with other state-of-the-art GN frameworks. We observed that FSGN can improve the best performed baseline RGC by 9% to 14%. There are many two reasons for this. First, FSGN adds H types into the process of representation learning. It can be regarded as a joint learning of H embedding and noding. Thus, FSGN can preserve the comprehensive program semantics based on interprocedural control and data dependence, improve the flow sensitivity for memory-related vulnerabilities. In addition, RGCN aggregates node and edge information through directed edge, while FSGN boosts the effect of edge types on context by adding corresponding inverse edges. Therefore, FSGN can effectively contribute to the performance of MVD, as it can better capture the structured information of vulnerable code. In RQ4, we account for the time cost and in seconds of each approach in training and detecting vulnerabilities. The results show that in comparison with the popular static analysis-based approaches, MVD achieves less time cost over other approaches, except PCA. This is because PCA speeds up data dependence computation through sacrificing partial detection precision. Compared with other learning-based approaches, MVD spends relatively longer training and detection time because in learning, complicated program semantics in graphs is more time-consuming than in sequence. However, MVD yields better detection results. Therefore, we can conclude that, in spite of a great deal of training time, MVD achieves relatively shorter detection time with better detection results, making a trade-off between accuracy and efficiency. Okay, this is all of our work. Let me make a conclusion. In this paper, we propose MVD to detect memory-related vulnerability statements that are related to sensitive operations. MVD employs a new graph neural network-based approach that leverages the flow-sensitive graph neural network to jointly embed both unstructured information and structured information for preserving type-level program semantics to learn implicit vulnerability patterns. The experimental results show the effectiveness of our approach by comparing our approach with three state-of-the-art deep learning-based approaches and static analysis-based memory detectors. That's all my presentation. Thanks for listening.